Hey everybody, sorry for the interruption at the end of the last screencast. Just continuing here with the discussion of bivariate distributions of continuous type. Want to do a little bit more with conditional distributions that we got started on towards the end of the last time. So I want to switch up the bivariate distribution on you so we can get a little bit more practice. Let's say that capital XY has the following joint probability density function. And that holds for XY is bigger than 0. So we're looking at a sample space that is the first quadrant. And let's just try to find the conditional distribution of capital Y given that capital X is some value little x. So you know that we're going to need f of xy over the marginal for capital X at little x. And so we'd better go ahead and get that marginal. So we'll stop and compute that. And that marginal by definition is the sum over all the y's of the PDF. And so it's this improper integral. And don't leap to just do it by substitution. Always check out to see if there is maybe a way out of computations. I'm looking at this and applying a property of exponents. And then I've got some stuff like this x and this e to the minus x that don't depend on the variable of integration. I'm going to choose to factor out the e to the minus x. I'm going to leave the x in, and you're going to see why in just a tiny moment. What I'm planning to do is to rewrite the integrand here. Instead of x's, I'm going to put 1 over 1 over x. Okay, so I've rewritten it like this. And then I stare at that and I realize, whoa, remember the PDF for an exponential is 1 over theta e to the minus x over theta. Whoa, this is actually the total area under the PDF for an exponential random variable where the theta parameter is 1 over x. Therefore, it must be 1. Therefore, the whole thing must come down just to e to the minus x. And that's good for any x bigger than 0. So before we go on to get the conditional of y given x, I just want you to notice this PDF, you could rewrite it like that. And then, whoa, x actually is an exponential random variable with theta parameter equal to 1. Woohoo! Now let's go for the conditional of y given little x. And so we start that computation again, all right? And it comes down to this, now that we know we can put an e to the minus x in the bottom. And so there's this cancellation. And I've got a typo here, which is very sad. What I'm doing here is trying to rewrite x as 1 over 1 over x and had a brain fart. So that should be a 1 over 1 over x. And similarly, this should be a minus y over 1 over x. And then that would be a correct rewriting of this. And so go ahead and scribble that down, scribble the correct thing down on a sheet of paper and look at it. And you're realizing that you're looking at the PDF for an exponential random variable where the theta parameter is 1 over x. So the conditional distribution of capital Y, given the capital X is little x, is exponential theta is 1 over x. Wow, it's kind of neat. How about the unconditional distribution of y? You know, what's that like? What's the marginal for y like? I won't be too ambitious. I won't try to get the whole marginal. I'm just going to get maybe could we find its expected value? And one reason I want to do that is just since we're already working with conditional y given x, this gives us another chance to use the conditional expectation formula, which we just love to practice with. So let's just try that. Expected value of y is expected value of the expected value of y given x. Okay. Well, y given x is this exponential theta equals 1 over x random variable. So its expected value is 1 over x, because the expected value of the exponential theta is a theta. And so I got to find the expected value of 1 over the random variable x, the expected value of the reciprocal of a familiar random variable, an exponential random variable. Can it be done? Let's see. So I'm looking for the expected value of a function of x, reciprocal of x. And so I know that I can just do sum over the possible values of capital X, the function of the possible value, so 1 over x, times the PDF. And that's an improper integral. Improper in, I guess, 2 ways. It's undefined at 0, and you're also going off to infinity. But it's the area underneath this function and over the x-axis. And I'm wondering, like, what is that area? Well, I'll know at least this. It's definitely bigger than the area under that same function from just 0 to 1. Now let me focus in on this. This function here, look at the e to the minus x part. E to the minus x decreases as x increases. When x is 0, it's 1. When x is 1, it's e to the negative 1. And it decreases in between, down to the e to the negative 1. So if I were to replace e to the negative x with e to the negative 1, I would have a smaller integrand. And so the area underneath it would be smaller than before. Okay, now let me just focus in on that improper integral. The e to the minus 1 I can go ahead and factor outside. So I can focus on this simpler improper integral. And I set up that improper integral. I approach the improper point 0 from the plus side with my little n variable there. And then I apply the fundamental theorem of calculus. The antiderivative of 1 over x is log ix. And then I evaluate between, n and 1. So I got log of 1 minus log of n, and I got to do this limit as n goes to 0 from the plus side. Now, log of 1 is 0. But what's happening with log of n? Well, n is going to 0 from the plus side. Think about the graph of log of x. It increases as x increases, and log of 1 is 0. And then it just increases slowly into infinity as x goes to infinity. But what we're concerned about is when x is like, getting near 0 from the plus side. And there we see that the log of x is a negative number, and it's got the y-axis as an asymptote. It's actually headed down to negative infinity as x goes to 0 from the plus side. And so actually, minus minus infinity is plus. The area underneath just this thing is infinite. So this expected value is infinite. It doesn't exist. So that can happen to you. And it happened here. This marginal random variable y has infinite expected value. Just kind of cool. Okay, another little application of bivariate distributions. I call it the problem of the broken stick. So say you got a stick, and you just break it at 2 random places. And so like where you break it the second time is independent of where you break it the first time. Could be further to the left or further to the right than where you broke it the first time, doesn't matter. And any of the 2 breakpoints are equally likely to occur anywhere along the length of the stick. When you do 2 breakpoints, you're going to have to break that stick into 3 pieces. 3 pieces will be the result of 2 breakpoints, right? And my question is, what's the chance that the 3 pieces can form a triangle? Sometimes it'll happen that they make a triangle, like if this is your stick here. And if this dot here is one of the breakpoints, and like here's another breakpoint. then maybe you got these three lengths. You've got a stick with length A, and a stick with length B, and a stick with length C that came out of it. And it looks like you could stick those together to make a triangle, maybe like that. But on the other hand, if your breakpoints leave a couple of the sticks too short, like here, one breakpoint and another breakpoint, then the B and C links are so short that they can't be made to connect together, when they're stuck on the ends of the A length. So what's the chance that you get a triangle? To make my computations a little simpler, I'm going to assume the length of the stick is 1 foot. And let's set up a bivariate random variable that's the pair of breakpoints, x, y. Now, x is like the first break I make, and y is the second break I make. I don't make any supposition about which one of them is bigger than the other. Either one of them could be between 0 and 1, anywhere, regardless of what the other king was, regardless of what the other breakpoint was. So how would I model that appropriately with a PDF? I suggest the following PDF is what we're looking for. It's 1 if x and y are both between 0 and 1. So it's going to be 1 over this square that you see here in the xy plane. That's our sample space, the support of the PDF. It's going to be 0 outside of that square. Now, why do I say it's going to have to be a 1 there inside the square? Well, any pair of breakpoints would be equally likely because each breakpoint is equally likely to be anywhere between 0 and 1, independently of each other. So I know that there has to be there ought to be a constant height for your PDF. If it weren't a constant height, there would be like some parts of the square where your ordered pair would be more likely to land, and other parts less likely. But it's supposed to be equally likely. So we need a constant there. But why a 1? Well, the volume underneath your PDF has to be a 1 for it to actually be a PDF. And so, like, say the height were a C, then the volume would be the height C times the area of the base, which is 1. 1 times 1 is 1. And so the volume is C. C would have to be a 1. So that's why I think this is the PDF that we need. Now, we want to find the chance of a triangle. So what we need to do is to represent the event that you get a triangle somehow more formally as a subset of this square. So it's a set of ordered pairs in this square. I'm going to call it A for short. And once we find that subset, the probability of landing in the subset would be the integral over that subset of the PDF. And so that would be the integral over the subset of a 1. And so it's the volume underneath 1 over this subset A. And volumes of things are their base times their height. So it would be the area of A times the height, which is 1. So it would just be the area of A. And I'm sorry for that stuff there that shows up. It's like bleeding through from the back side of the page. Sorry about that. Okay, so now we know that if we just get A and find its area, then we would have our question answered. All right, now let's get down into finding A. It's really helpful to remember the law of triangles, from middle school geometry or something. If you've got 3 sticks of length A, B, and C, they can form a triangle if the sum of any 2 of the lengths is bigger than the 3rd length, and vice versa. It's an if and only if relationship. So you would need these 3 inequalities to hold. A plus B would have to be bigger than C, and A plus C would have to be bigger than B, and B plus C would have to be bigger than A. Okay, So take a specific breaking somewhere inside that square, say little x, little y. There's two cases we need to consider. We first need to consider, like, if x were less than y, what would have to happen for us to get a triangle? And if x were bigger than y, what would have to happen for us to get a triangle? So let's focus in on case one to start. If x is less than y, you think about your whole stick as the thing from 0 to 1 here, then the breaks have x to the left and y to the right. And so your three pieces, there's one of them that would have a length of x minus 0, or x. This middle one would have a length of y minus x, and this right-hand one would have a length of 1 minus y. And to get a triangle, you would have to have the triangle law applying. The left and the middle would have to make more than the right. The left and the right would have to make more than the middle. And the middle and the right would have to make more than the left. So you got three inequalities, and what I'm doing is just working with each of the inequalities to get something simpler. And I come up with these three things. Y is bigger than a half, y is less than x plus a half, and x is less than a half. In case two, the pieces would look like this. And so their lengths would look like y and x minus y and 1 minus x. And if you apply the triangle rule to those three quantities, similar reasoning would give you this and this and this. It's the same as before, except the x and the y's got switched around. So you shouldn't have to go through that reasoning. You can just say similar reasoning because of the symmetry of x and y. But this middle one, I kind of prefer to solve it for y in terms of x. So that's the one I'm actually like boxing in for later reference. Okay, so we got all like these inequalities to consider. And so to identify our event A as a subset of the square, it might be helpful to graph the square. And so that's that kind of like shaded in stuff here. And also graph the equal versions of all those inequalities. So like y equals a half, x equals a half, y equals x minus a half, y equals x plus a half. Go ahead and graph them all. And hey, graph y equals x as well, because we've got the x less than y and x bigger than y cases to think about. So I've got those lines, those horizontal, vertical, and sloped lines, all trying to draw them in here. And so let's think about it. What at case one, where x is less than y? That would put you in the top triangle of the square, the one that runs from 0, 0 to 0, 1 to 1, 1. Anywhere in that top triangle, the x has to be less than y. And the reason is that along the line y equals x, the x is equal to y. But for x to be less than y, it means you need to move, you would be moving to the left a little bit. And sure enough, that would put you in the top triangle. Okay, so let's think about it. When x is less than y, what else has to happen? Well, it's these three things. And so from the first thing, your point's going to be more than half a unit high. It's got to be less than halfway through the square. And also the height has to be less than y equals x plus a half. And this little kind of shaded in triangle is showing that. That was what was bleeding through to the other side. This little very heavily shaded thing is exactly those three conditions put together. And then when the other case, when x is bigger than y, you got to think of these three box things, and they all have got to happen at once. So x has got to be bigger than a half, but y has to be less than a half, which puts you in this kind of like bottom square that I'm waving. But on the other hand, y has to be bigger than x minus a half, so you have to be above the y equals x minus a half line. And so you get that other little blacked in triangle. So you get this butterfly-looking shape. That is A. What's its area? Well, those two triangles are 2 out of a total of, count them, 8 congruent triangles. 2 out of 8 is 1/4. So without any like base times height type of math to get triangle areas, we just see that the area has to be 1/4. It's 1/4 of the area of the whole square, which was a 1 in the area. So if you break a stick randomly in 2 spots, there's a 25% chance that your 3 little resulting substicks make a triangle. That is cool. Final chance to practice. How about number 15 in the section? So this one is about like an auto mechanic. And people bring, things for him to repair, and he makes an initial estimate, and then he has a final cost. And, the final cost for, it's always, a little bit off of the initial estimate, but it's equal to the initial estimate on average. Sometimes higher, sometimes lower, but on average equal to the initial estimate. Now, let's say his initial estimate X in thousands of dollars is given by this PDF. 2 times e to the negative 2 times x to the minus 0.2, 4x is at least 0.2. Okay. I can rewrite that. I can write the 2's as 1/1/2's. And then when I stare at it, it looks like a shifted exponential random variable. It looks like the theta is a half, but instead of going from 0 to infinity, the possible values for x are from 0.2 to infinity. So it's really like take an exponential random variable with theta equals a half and add 0.2 onto it. That's really what this random variable x is like. It's 0.2 plus an exponential theta equals a half. Thousands of dollars. Okay. So theta equals half, the mean of that, it'd be the theta to half 1,000, $500. Plus a 0.2, 0.2, $200. So on average, the estimates are $700. Now, what's the actual cost? Well, the actual cost depends on the estimate, and then it'll be the estimate, give or take some. Let's say that the actual cost, y, given that capital X is some value, is uniformly distributed, with a low of capital X minus 0.1 and a high of capital X 0.1. So that means his final cost is equally likely to come anywhere within $100 of his initial estimate. Could we find the expected value for the final cost? We are ripe for using conditional expectation formula. So we are looking for the expected value of the expected value of a uniform x minus 0.1 to x plus 0.1. What's the expected value of a uniform? It's the low plus the high divided by 2, right? So you got to do x minus 0.1, x plus 0.1, add them together. That would be a 2x. Divide by 2 is an x. So we're really looking for the expected value of just capital X. Well, capital X is this funny shifted random variable. Here's the definition for its expected value. Integral over possible values, x times the PDF. And, that would be a doable but kind of yucky computation because I'm seeing maybe a need for integration by parts here. But being the lazy person, I did reason out that this random variable was distributed like 0.2 plus an exponential with theta as a half. the expected value of such a random variable would be the expected value of 0.2, which is 0.2, plus the expected value of that. So 0.2 plus a half, 0.7. Okay, $700. So there it is. You'd expect them to charge you $700 on average. Give or take how much? What would be the standard deviation of this random variable? Well, we could get its variance. We could do that with the conditional variance formula. So we need the expected value of the variance of y given x. Y given x is a uniform. And remember, the variance of a uniform is high minus low squared over 12. High minus low this time extends 0.2. Something plus 0.1, something minus 0.1. 0.2. Square it over 12. So we need the expected value of that. That won't be hard. We also need the variance of this expected value, the expected value of y given x. Y given x was uniform. The expected value was right in the middle. It was x. So we need the variance of x. All righty. Well, the expected value of a constant is constant. So I got a 0.04 over 12. But how about this x deal? Well, the x is distributed like 0.2 plus an exponential, theta is 0.5. So let's think about how this works. The variance of a constant plus a random variable, that constant just moves everything up by 0.2. It doesn't change how spread out the random variable is. It just moves up its possible values. So adding on a constant should not change the variance. We will formally prove that kind of thing later when we collect all properties for expected value and variances. But we'll find, we'll be able to prove that. So really, we just need to find the variance of that exponential. But the variance of an exponential is the theta squared. So 0.5 squared. So 0.4 over 12 plus 0.5 squared. 0.25 plus not much, about 0.28 roughly. Square root of that, a little bit more than 0.5. So I think we're looking at expecting 700, give or take, about 500 or so. So there's actually quite a range. You could have a very cheap repair, you could have a pretty expensive repair. We've got to replace the whole engine in several $1,000s. Well, that seems to be about it for the examples in this section. So we'll call it a day and see you soon.